This is Lab 3, Magnetic Field of a Bar Magnet. An introduction. So the purpose of this lab is to measure the distance dependence of the magnetic field due to a bar magnet. We will compare our data to equations we learned in class for determining the magnetic field of a magnetic dipole. Models and principles. This lab incorporates the idea of the magnetic field, which is similar to the electric field except that the magnetic field is caused by the motion of charged particles. The lab also deals with the magnetic dipole. And through this lab, we were able to experimentally determine a value for the magnetic dipole moment of the magnet, as well as model the relationship between distance and the magnetic field of a bar magnet. Models. Magnetic fields come from the movement of charged particles. The law that relates the magnetic field to distance is called the Biot-Savart law. There are a couple different variations of the law, but we want to use the one that approximates the magnetic field of a dipole on its axis, as well as the general formula for the magnetic field of a dipole at any observation location. In order to model the relationship between magnetic field and distance, we conducted an experiment using a magnetometer app on a smartphone to measure the distance at which the magnetic field was equal to some amount. Before doing that, however, we first had to align the phone with the Earth's magnetic field in order to measure only the magnetic field of a magnet. We did this by rotating the phone on a flat surface until the x component of the magnetic field was 0. Then we had to find the location of the magnetometer on the phone, and we did this by placing the bar magnet on the axis perpendicular to the phone and sliding the phone vertically to find the location where the measurement was strongest. This was done in both the horizontal and vertical directions to pinpoint the location of the magnetometer. After calibrating the phone, we started to measure the distances at which the magnetic field was equal to some number. We started with 70 microteslas, so we slid the phone along the perpendicular axis until the x component of the magnetic field read 70 microteslas. This was repeated for various values until we had enough data to create a model for the relationship between magnetic field and distance. The Biot-Savart law equation for the magnetic field of a dipole on the axis of the dipole can be written as shown. The variable n is what we are looking for in this case. By taking the natural log of both sides of the equation, we are able to linearize our data, with n being the slope of the line. The experimental value of n in this case was n equals negative 3.2, which is close to the expected value of negative 3. To calculate the magnetic dipole moment, we replaced k with the constants in the Biot-Savart law and solved for mu, which we found to be 1.66 amp times meter squared. And for part 2 of this experiment, we went out a horizontal distance from the magnet such that the x component of the magnetic field was 100 microteslas. Then we went up vertically by that same distance and measured the x, y, and z components of the magnetic field at that position. This resulted in an experimental value for the net magnetic field of 8.71 times 10 to the negative 5 teslas. And after obtaining an experimental value for an off-axis magnetic field, we wrote a program using a general approximation for the magnetic field due to a dipole at any observation location. We created a function that calculated the magnetic field at an observation location and used it to model the magnetic field at 2 locations on the dipole axis, 4 locations on the perpendicular axis, and the location of our off-axis magnetic field from our experiment. The magnitude of the off-axis magnetic field, according to our program, was 1.89 times 10 to the negative 5 teslas. And discussion and conclusion. So for the first discussion question, says, what if you hadn't oriented your experiment to compensate for magnetic north and had instead laid out your meter stick at some intermediate angle with respect to Earth's magnetic field? How would your results have changed? My results would have been less accurate, as the readings for the magnetic fields would have been affected by the Earth's magnetic field. The expected relationship between distance and magnetic field could have been altered. And what if you were to stick 2 identical magnets together end to end and run the experiment again? How would you expect your measurements to differ? I would expect my measurements to all increase. Instead of having 1 magnetic dipole, we would have 2 magnetic dipoles superposing their magnetic fields on the observation locations, therefore causing an increase in the magnetic field measurements. And to conclude, we measured the magnetic field of a bar magnet at different locations to accurately model the relationship between distance and magnetic field of a dipole, calculated the magnetic dipole moment of the bar magnet, and measured an off-axis magnetic field which was compared to a computational model.